Welcome everybody to the first meetup that we have for 2021. So excited to kind of kick things off this year. We've been missing doing these meetups, and unfortunately we couldn't do January due to unforeseen events. But yeah, we're back, and I'm so excited to just bring you awesome talks as we always do. This month, we've got Steven Waterman. For those of you who have been to our physical meetups, you might remember Steven from his previous talk where he launched sweets into the crowd and gave concussion to just a few people. But before we go any further, I just want to kind of introduce NDTech. So all the new members, we are a tech agnostic group, and we are here to create a safe space essentially for techie people to discuss technical ideas. So by safe space, what I mean is we don't allow selling or recruitment. So don't worry, you're not gonna get jumped on by a recruiter or anything like that. We're just here to talk about tech stuff and provide you with awesome content. Who are we? So yeah, if you don't know us, I'm Chris. I know my name actually says Mark. That's because I'm actually stealing his account tonight. Hopefully he doesn't actually know, but yes, I'm stealing his account tonight, but yes, my name's Chris. We've also got James and Martha who are on the call. Feel free to shout out and give us a wave. This is usually when I would point them out into the crowd and embarrass them. So yeah, if you want to kind of get in touch with any of us, got those social media handles there. If you want to get in touch with anything about any tech, so not just any one of us, then any tech, we're all over social media, and we've got a website there, any.technology. We also have a Discord chat. Obviously, I don't expect you to remember that unless you're a genius. But yeah, go to the website. That's the easiest way. And there's a little link at the top where you can get on that Discord channel and ask us any questions you like. Or if you have any feedback for us, it doesn't have to be any questions. What basically makes these meetups is you guys who join it. Without you guys, we wouldn't have a meetup essentially. So if you have any feedback for us or any of the speakers at any time, obviously we've got Steven coming up. Please do get in touch. Equally, if you want to speak at any tech, or you've seen somebody at a conference or something that you might want to kind of see speak at any tech, then yeah, do get in touch. Big thanks to our sponsor, Scott Logic. Usually when it's a physical meetup, we do have drinks and food available, but obviously, pandemic's kind of stopped that, and we've moved to virtual meetups. But yeah, with Scott Logic kind of behind us, it keeps us going. So yeah, big thanks to them. So yeah, our speaker for tonight then, enough about any tech. We've got, yes, Steven Waterman. He works for the NHS, and he's going to be discussing how he used voice recognition to help him edit audiobooks. Awesome talk. If you want to get in touch with him, he's on Twitch. I'll give a shout out to his Twitch channel there, Steve Waterman. On Twitter, same thing, Steve Waterman. Definitely get yourself on there, and he will he'll be sure to kind of keep you entertained with his live coding or anything to do with video games, I guess. But anyway, without further ado, I will hand over to Steven, and yeah. So yeah, feel free to take the screen.
Fantastic, I will.
There we go.
There we go. Is that working? See that?
Yep, all good.
Fantastic. Okay, I guess I'll just get started. Hello, again, you've stolen half my intro, but I'm Steven, software developer at the NHS. I know all these guys because I used to work at Scott Logic, and that's where I did this that's where I did this talk for the first time. First of all, very important, I'd like it to be known that I made a special effort not to wear pajamas. That is, I think that's high praise for how much I value being here. It's a rare occurrence nowadays. I hope that you're all having a good day. Thank you all for coming along to watch, and thank you to the folks at AnyTech for having me back and inviting me to speak after I launched Quality Street at the man's face and a fire sprinkler in the ceiling. Thankfully, it didn't go off, though it would have dramatic effect, Have a look on YouTube. There's a video of that talk. It was chaotic. Today, okay, no, before that, I don't mind being interrupted. If you do want to ask questions, or if you don't understand anything, you can stick them in the chat. I'll respond. Alternatively, you can just unmute yourself and I'll pretend that it's a work call. So yeah, at least that way we can prove that this isn't just a pre-recorded video. Let's try and have some interaction. Today, I'm here to talk to you about Narration.Studio. Narration.Studio is a side project of mine from a few months ago. Like many of my side projects, it was born out of a frustration at having to do something manually. It all started when I was writing what is probably my favorite blog post ever, Down the Ergonomic Rabbit Hole. I think, yeah, there we go. This blog post, and I really do suggest that you go and read it later, is a 5,000 word love letter to my weird keyboard. There you go. Don't know if you can see that. Yeah, do read the blog post to learn more about that. So 5,000 words, and it was quite unlike anything I'd ever written before. It was really narrative, like I was telling a story, and it was a lot more lighthearted. And it kind of felt more like a tech talk. It was full of terrible diagrams I drew in MS Paint. And it didn't really feel like a lot of my other blog posts, which were very technical, very hard facts, and here's how you do this. It was more just me telling a story. I thought, why can't it be a tech talk? Why don't I just record myself reading the blog post? So I did. I recorded myself reading it, and I just put a little audio element in there. And you see 33 minutes long. Go watch it though. Listen or read. The only problem with that was that it wasn't very easy to follow along with the text as the audio was playing. It's a 5,000 word blog post. It was quite long. You had to scroll through it and try and keep up and find out where I was. So I thought, well, how about we have it auto scroll in time with the audio so that it shows you which bit that you're currently looking at. And I was going to show you it live, but I can't get my desktop audio to go to you. So here's a picture. Basically, it just highlights it. I mean, I guess I can show you what it looks like. It looks like this. Here you go. It just kind of scrolls through based on where you are. Let's try and get that to present again. I wasn't meant to close that. It wouldn't be a tech talk without tech issues. There we go. So, like that, basically. In order to get that to work, I needed some way to link up the audio with the text to say which bit of text happens with which bit of audio and vice versa. So I did what any other tech mad person would do and manually wrote down timestamps for every single paragraph. As you can probably predict, that was incredibly tedious. It was an incredibly tedious 1 to 2 hours of my life. So I spent the next 2 weeks creating Narration.Studio to automate that process, which was a move that definitely saved me time in the long run, definitely. But I've kind of told you why Narration.Studio exists, but like, what actually is it? Well, it's a spectre which haunts me in the night when I wake up. It's a lot of complicated tech crammed into a fairly small package, and for a fairly simple output as well. Basically, what it does, it's a browser app that takes a markdown file. So I write my blogs in Markdown. takes one of those as an input. It asks you to read it and records you while you do so. And then it automatically edits that audio, cutting out any pauses, any bad takes, produces a finished audio file, rendering it losslessly, and it adds timestamps into your markdown. Essentially, it automates the entire pipeline of adding audio into the blog post, other than the bit where you have to read it. It doesn't sound easy. It certainly doesn't sound trivial, but it doesn't sound that hard. I made it a lot harder by making some pretty bad design decisions. Not bad, ambitious design decisions. Bad design decisions what made it harder. So first of all, I wanted it to be client-side only. That's better for the user's privacy. There's no worry that, I'm going to be listening to them speak, and they can check the network tab if they wanted to prove that it's never leaving their browser. And also I'm cheap, so I didn't want to pay for a server. I also wanted it to be a browser app. I could have just made like a desktop app. That would have been easier. There are more libraries for desktop speech recognition. But I like browser apps. I like websites. They're nice, and it's kind of the only front-end development that I can tolerate. So that means that everything, remembering that there is no server, everything needs to happen in JavaScript. So we're talking about real-time speech recognition and lossless audio editing here in JavaScript in a browser. And if that wasn't hard enough, I also wanted it to be hands-free. And by that I mean, when I'm recording it, I don't want to give it any input. I don't want to have to touch the keyboard or the mouse. Ideally, I don't want to have to use any like control words. I don't want to say done. I don't want to say like next or back or try and tell it which sentence I've said. I just want it to figure it out. And that certainly makes for a better user experience, but made for a difficult developer experience. Yeah, if I have to mark which bit of the script I'm saying at a given time, what's the point? Just do it manually at that point. So yeah, hands-free. I want no backend. I want it completely in JavaScript in the browser locally, and I want it to be hands-free. Sure, that won't be too hard. That was a lot to take in, so let's just see it in action. You can try it out for yourself. It's just Narration.studio. I even bought a domain name for it. But other than that, I'm going to show you it kind of in the on the screen here. So here is what Narration.studio looks like, and you will need to use Google Chrome as well if you're trying it at home. Bearing in mind that you should try it at home, because I can't show you what it sounds like because I can't send you the desktop audio. But pretty much the way it works is you click Start Again, and this is the first screen. There are 3 screens in this app. Each one is doing something complicated, and we're going to be talking about the middle one, but I will show you all of it. So this first screen, all it wants you to do is paste in the script that you're going to read, and I've written one especially, just like that. And it supports Markdown. It supports GitHub flavored Markdown, so you can use things like footnotes and whatever. So yeah, we put the Markdown in there, and you click Submit, and then you can probably imagine it's then having to do some kind of Markdown compiling and transpiling and interpreting and all of that in JavaScript in a browser locally with no server. Kind of complicated, but that's not the bit we're focusing on. Click Submit, and it has separated out one sentence. It's that first sentence. And you can see that it's running now. It is currently recording me. It is saying what it hears. You can see it down at the bottom there. There we go. And it's saying what line it wants me to say currently. And you can see that there are some buttons, very far left, very far right, and kind of bottom middle. Those are your overrides. I want it to be hands-free, but it's better that you can manually override it in the case that, it just can't understand what you're saying. So I guess I'm going to start using it now. And it has been recording the whole time. So all I have to do is essentially say what it says on the screen. The script to use in my tech talk. So I've said that first line. It's recognized that I've said it, and it now gives me 2 lines that I can say. If I didn't like how I said that last line, say I said it wrong, I can just say it again. the script to use in my tech talk. The script to use in my tech talk. So there you go. I just said it 3 times. It's seen it all 3 times. It's taken the last one. When I'm happy with that, I can just move on to the next one. So the next line. This is the text I'm going to read aloud during my tech talk. It's not the most interesting text. Nevertheless, I think it should serve to prove a point. Now, hold on to your hats because we're about to see something crazy. No, I didn't like that. I'm going to say that again. Now hold on to your hats because we're about to see something crazy. This is a new paragraph. Wow. We saw a new paragraph, guys. That was exciting, wasn't it? Truly innovative content this is. Okay, and that we've come to the end of the script and it says, so when we're done, we can just say completed. Completed. There we go. What you're watching now is live audio editing in browser, and now we're on to the third screen. This is a whole load of WebGL. This page is like 90% rendered on the graphics card. You can pan around, you can zoom in to the point you see the entire waveform, and this is kind of your fine tuning. You can just listen to it by pressing play or pressing space, and I don't think you can hear this, but I can. So pretty much what it's doing is for every sentence that it has asked me to say, it's taking the last take that I did of that sentence, cutting out everything except that, putting them together with pauses between them based on, so things like the heading has like a 1-second pause, while the normal just between sentences have like 0.35 seconds. And then here's another paragraph, that's 1 second. And yeah, you can just kind of click through it and go wherever you want. And you can also see here, this is the script that we put in, and it's gone through and it's put in these timestamps for us. So those are the exact timestamps. And in fact, if I say, if we go over here and I change this, you can see the timestamp is changing in real time because the time in which that audio happens is changing. And let's say, one of these, I don't know, yeah, there's a good example. Just here, there's a little bit of audio here, which I don't want. Well, you can just click, drag, and adjust, and then adjust the end as well. You can make it longer and shorter, and that's it. So this is just for fine tuning, really. And I'm not going to go too much into detail on this. It's just a lot of WebGL code. You can have a look on GitHub if you really care. The final point of this is that you can press this button, and it will download a finished WAV file, kind of editing these bits together for you. And that's Narration.Studio. So let's go back to the presentation. That's the wrong one. We'll get there eventually. I don't even know what I did there. There we go. Right. Okay. Excellent. So that was the demo. As I said, it's made up of 3 screens. Each one has its own fiddly and annoying things, but we're focusing on that middle screen, the one where I was actually speaking. That screen, it's not complicated in what it's doing at a very high level. It's taking a list of sentences. So that first screen, you put the markdown in, it's compiling it to the list of sentences that it wants you to say. That's your input. That comes into this second screen. And as an output, we want essentially a mapping of the start and end of each sentence in this audio that we've also recorded. It's simple conceptually. It's quite difficult once you try and break it down. There are 2 important parts. So we need to know what the user said in the recording. So in the audio, what did the user say? It's probably going to be the blog, but we also need to know when they said it, the start and end of each one, so that we can cut it and kind of paste those bits together. So the first problem, how can we detect what a user is saying? We'd need to write some kind of really complicated audio analysis code and then break out each like phoneme in the speech and make sure that it works on all different kinds of accents and make sure that the performance is good on really bad hardware, and or we just use the speech recognition API that's built into Chrome. So that makes things a bit easier, kind of takes the fun out of it, doesn't it? But no, there was still a lot of complexity, don't worry. So is this speech recognition API widely supported? It says it's experimental. Right, that's not good. Well, I mean, it's not great, is it? No browser fully implements it. But Chrome's had it for the past 60 versions or so. So at least I'll only have to support one browser. It did mean that I had to do the one thing that I really hate in web development, which is a big red mark on the website if you try and visit it in anything other than Google Chrome. And I mean, you can see here that I was very apologetic, saying I normally ignore these as well, but I'm not going to physically let you ignore this because it just won't work. So how does this speech recognition API in Chrome actually work? The first step, pretty simple. You just ask Chrome to start its speech recognition engine. You tell it to start recording and start letting me know. So you say, let me know when something is gonna, let me know when things happen. When it first starts recording, it sends this audio started event. And that just means it's listening. When it detects that you started saying something, it sends you this speech started event. And then when it detects that you've finished saying something, it sends this speech ended event. A little while after that, once it's done some processing, I guess an important point to note here is that Chrome is actually using a backend server. So the speech recognition API in Chrome is implemented so that it sends requests to Google servers rather than doing it in the browser. I didn't really have much choice. I don't like it, but it is what it is. So there's a little bit of a delay there after the speech is ended while they process it, determine what you've said, and then you get the speech recognition result back. And then once it's happy that that result has come in, it stops recording and sends that audio ended event. Generally, this gap is around half a second, 500 milliseconds. So this does, it only works one line at a time. You ask it to start recording, it will record you for one sentence until you stop talking, it'll tell you what you said, and then you'll have to start it again. It's not a kind of continuous stream. So all of those events that we saw, all of those events there contain timestamps. But the result, the speech recognition result, has some other information that we're interested in. So we obviously get the timestamp, but we also get the transcript along with a percentage confidence of how sure they are that that's what you've said. In Narration Studio, I only ask it for one option of what it thinks that you've said, but you can say, give me the top 5 with each confidence interval for each option. So in the end, this is kind of what it looks like when I'm talking to the API. So I'll do audio started, and these milliseconds are relative to the page load time. It's just the default HTML event timestamp that it uses. So 30 seconds after the page was loaded, it started recording. A few hundred milliseconds after that, I'd heard the start of some speech. The speech lasted not very long at all, kind of 100 milliseconds. Those are some bad numbers I've made up. A little while after that, I think I'm off by a factor of 10, aren't I? Yeah. A little while after that, we get a speech recognition result. And it says something like, I'm 98% confident that the user said, welcome to my blog post. And then a little bit after that, it stops recording. So here's what we see. So we get the speech recognition result back, and it'll be something like, after 30,000 milliseconds, I know what the speech was. I'm 98% confident that it was, welcome to my blog post. However, this is quite unrealistic. In practice, it tends to be more like this. I'm 70% confident that the user said, welcome to my blog post. And that's where it all starts to fall apart, because it isn't as simple as just using the speech recognition API, detecting when they've said the thing that it says on the screen, and using those timestamps. So in that case, how can we detect what line the user said? as you saw in the demo, there were two lines, two options. There was the previous line, the thing that I'd already said, and there was the current line, the thing I was going to say next. The speech recognition API thought it heard "welcome to my blog post." Is that closer to option 1, welcome to my blog post, or option 2, this is the second sentence? I think as humans, it's pretty obvious. But how to do it algorithmically isn't as obvious. I clearly paid attention in my second year of university when I learned about Levenshtein distance in the algorithms module, because that was the first thing I thought of. Levenshtein distance is a way of comparing two strings and getting a number to say how similar they are to each other. It's based on how much you would need to edit one of the strings to convert it into the other one. It's also known as edit distance or string edit distance. So let's take my name. How similar is my name to the word Stephanie, or the name Stephanie? Well, the Levenshtein distance is 5. That's kind of meaningless on its own. I mean, you can see here, it's 5 because there are 5 edits that need to be made. An edit can either be changing a letter, adding a letter, removing a letter. There are kind of tuned versions where you'll say changing a letter is cheaper than adding or removing a letter, things like that. But anyway, the distance is 5, and that's kind of meaningless. But it's not meaningless when comparing to something else. Stephen has a distance of 5 to Stephanie, but it has a distance there's a much bigger distance to the word dinosaur. You need to make a lot more changes. So we can see that Stephen is closer to Stephanie than it is dinosaur. So let's just use Levenshtein distance to determine which sentence the user said. Welcome to my blog post is only 3 edits away from welcome to my blog post. There's, we need to stick an L in, we need to get rid of the D on the end and change the E into a T. But it's 22 edits away from this is the second sentence. So yeah, option 1 is much closer. That's good enough for me. But Levenshtein distance doesn't always work as well as you might hope. Let's say the speech recognition system heard "it gave me pause," as in like a cat. And there are 2 options of what I might have actually said. I might have said "it gave me pause," as in it made me stop and think for a minute. Or the other sentence I could have said is "it gave me jaws." I'm not sure what context that might happen. Perhaps like a vending machine with DVDs in, you got jaws. Anyway, frankly, that's not the most nonsensical one. The one that we'll move on. "It gave me pause" is only 1 edit away from "it gave me jaws." There's a P, it becomes J. But "it gave me pause" is 2 edits away from "it gave me pause." They sound exactly the same. So perhaps this isn't the best way of doing it. How can we look at a sentence like that one? I don't know if you could tell here, I was meant to lead into that blank screen. How can you tell how a sentence is going to be pronounced? How can we tell that this sentence is going to be pronounced the same as that sentence? You can't. You see, I jumped the gun a bit. You can't. There's no easy way. There's no algorithmic way to look at a sentence and know how it's pronounced. There are some like really rough ways. There were some ways I think in like the late 1800s in America when they were doing the census, they wrote people's names in like a weird pronunciation system, and that was algorithmic. But there's no good way. But actually, there aren't that many words. And I know that sounds silly, but like there's only like 100,000 words that we kind of realistically use. So we can just use a big lookup table of every word and how it's pronounced. So the CMU Pronouncing Dictionary is a list of most English words and the phonemes they're made of. So phonemes are like mouth sounds. It's like an alphabet for sounds. So rather than it being letters, it's like, oh, that's a phoneme, and that's another phoneme. They come in like a little table. It's very exciting. Anyway, here they all are. So we've got like odd, the O sound in odd is written as AA in the CMU pronouncing dictionary. We've got, I mean, you can see things like the same letter. Is there a good example here? I guess it's things like the letter C can be pronounced as this phoneme K, or it can be pronounced as this phoneme S. So these are all the phonemes, and essentially it's just a lookup like this. So it gave me pause is it gave me pause, and it does try to map to, you know, something that you could read. And it gave me pause is pronounced the exact same way if we go through and translate each word in the dictionary. And then it gave me jaws is pronounced differently. We've got P and then JH here. So you can see that the top two are identical, and the bottom one is a little bit different. So can we just run the Levenstein string comparison on these strings instead? So comparing this string, this top one, to it gave me pause here and it gave me jaws. Yeah, in this case we could. And it would determine that, you know, the top two are identical, and then the top and the bottom are a little bit different. But we would have some issues, because it'll say that some phonemes are closer to other phonemes than other phonemes, if that doesn't make sense. But basically the problem is the changing from a T to IH is a string edit distance of 2, whereas changing from T to G is a string edit distance of 1, because the problem is that not all the phonemes are one character. If we give up on making the phonemes pronounceable, then suddenly all the phonemes can be one character, and we can just map each phoneme to a single randomly assigned character, join them all together, and here we have a string which is almost like a hash representing how these sentences are pronounced. If we run the Levenstein distance on those, then we get this. It gave me pause has a distance of 0 to it gave me pause, and it has a distance of 1 to it gave me jaws. But it's not always as obvious as that. In this case, the speech recognition algorithm did quite a good job of detecting what I'd said, and it got the pronunciation exactly correct. But what about in this case? It thought I said it says the laws, but I either was trying to say it gave me pause or I gave the jaws, and both of those are a bit off. This one is a distance of 5, this one's a distance of 6. So 5 phonemes need changing, 6 phonemes need changing. Do we just go for option 1 because it's lower? Well, probably not. And the actual selection criteria that I implemented was a lot more complex than just pick the one with the lowest Levenstein distance. The first thing that we do is calculate the distance, as we saw. So a distance of 5 and a distance of 6. I then convert that into a relative distance to say essentially how much of what you have heard has to be changed. Because the problem is that if I just say an arbitrary bounds of 3 edits are allowed, then in a really long sentence, 3 edits are barely anything, and in a really short sentence, 3 edits is the whole thing. So we convert it to how many of the phonemes need to be changed. And that can go above 100 if you're adding a lot of phonemes. So this is like a measure of the percentage of the sentence that needs to be changed. Then we actually use this confidence value as well, because if the speech recognition was 100% confident, then I'd feel more okay with going for option 1, even though it's 5 versus 6. If it had a confidence of 20%, there's no way I'm comfortable that that one margin is enough to be sure that it's this one and not the other. So we take that confidence and we apply it as like a confidence interval over the relative distance to give us the bounds. So if it's a 70% confidence, then I'm pretty sure it's going to be between 35, 71% relative distance. And for option 2, 47 to 95. Plot those on a number line, and if they overlap, we're not sure. So higher confidence will kind of make them much smaller and kind of tighter bounds, which means that they won't overlap, and the same kind of a bigger difference in distance, i.e. if one's much more confident than the other, then again, they won't overlap because they'll be further apart. And if they don't overlap, we just take the one that's closer to 0, i.e. closer to 0 changes. That's a lot to take in. It's not really that important, but it was kind of the final piece of the puzzle of how I go from just having the distance to actually being able to determine, Stephen has said this, or he said this, or if they overlap, we're not sure. And we did see that kind of when I was demoing it, when I was just talking to you rather than actually reading the sentences, it was a really long distance from both of them. So the yes, that's another bit that I've missed. Oh, okay, there's another slide. Hang on. Yeah, here's an example where it's more confident. The distance is 5 versus 12, and it's more confident that they're tighter, they don't overlap. And the final thing that I did was put a hard boundary at 50% to say if neither of them are below 50%, we're not taking it, because that's probably just the case that I've said something that isn't anywhere near either of them. Because if you need to change more than half the sentence, it's probably not right. So that's it. That's the whole speech recognition system, all the way from actually sending the request to the API, asking it to start recording, to we know which of the two sentences the user has said. So we know what they've said, but when did they say it? When was the start and end of them saying that sentence? Is it as simple as just looking at these speech events? Because I mentioned before they have timestamps. So can we just use those timestamps? No. The problem is, because this is running on Google servers, there's always going to be a latency between me actually starting to speak here and the speech started event happening, because that audio has to go to Google, get processed, and then come back to me as an event, and then get processed by the browser. Can we just add an offset to account for that latency? Well, no, because it's entirely dependent on how good your internet is and how high or low your ping is. If you've got a really bad ping, there's going to be more of a lag as it goes to Google and comes back. And in fact, it can change during, even like between the speech started and speech ended, your ping can change if there's more network congestion. So if we can't use this, what can we use? Well, it would have to be something recorded locally so that we could actually not have to have anything ping dependent. And the main thing is, well, we have access to the speech itself. If this is a clip of me saying something, I think to people who have played around with audio editing before, it's fairly obvious that if Chrome comes in and says this is where it ended, not really. It's more likely to be around here. This just looks like background noise. The speech has stopped. This is just a bit of latency. So the speech starts and ends when it gets loud and then it gets quiet. That's fairly obvious. That's how I would detect speech. If someone says, wait until I've finished, I'll wait until they are quiet. Why are we overcomplicating it? Why don't we just look at when it's loud, look at when it's quiet? Well, how do you detect silence or even just quiet? Well, it's when there's no noise. Yeah, but how do you detect that there's no noise? Like, the immediate thought is that you just look at the audio file and you look for the bits where it's zeros. But that's not how audio works. Audio files are just a bunch of numbers, and they're not how loud is it at a given point. An audio file, like a WAV file, is 44,100 floating point numbers per second. Each sample is a number, and on its own, it tells you nothing. Each sample is an instruction to the speaker cone of how far in or out it should go. A speaker cone being all the way out isn't loud, and a speaker cone being all the way in also isn't loud, but a speaker cone going between those really fast is really loud. So actually what we need to care about is how fast it's changing. I mean, look, here's an example. That sample there is a value of 0.75 in the file. It is the intro to Rick Astley's Never Gonna Give You Up, played at maximum volume. Also a value of 0.75 is this, which is silence offset 0.75 upwards. The only difference between this and silence is that this has like electricity running through the electromagnet in your speakers and wastes energy. So clearly we need to be looking at how much this value is changing. And to do that, we run the audio through a series of filters. So we start off with this. This is what our audio looked like to begin with. The first thing that we do is run it through a bandpass filter. What a bandpass filter does is says that only some frequencies of audio are the ones that we care about. So they're less commonly used. More often you'll see things like a high pass or a low pass filter, which say everything like get rid of the frequencies below this frequency or get rid of the ones above this frequency. A bandpass is kind of the opposite of those and doing both at once. So say get rid of everything above this point and below this point. That has a couple of effects. First of all, well, yeah, the first big advantage is that it gets rid of things like wind. So if you look at this, you look at the previous one, there's a load of these really, really low frequency oscillations up and down. Those are completely inaudible because they're too slow for human hearing to hear them. They're too low. What it is, it's changes in like air pressure coming in and hitting the microphone. And then like, a second later, they'll come back. And it just means that your audio is kind of going like this all the time. But that's not loud. We can't hear it. What we do care about is human speech. And human speech is pretty much solely between the frequencies of about 300 and 3000 hertz. It sounds horrendous if you only keep those ones because you get rid of all the like harmonics in the voice. But we're not going to be listening to this. We're only using this to detect the start and end. So we just get rid of everything that isn't between 300 and 3000 hertz. That has the added bonus of getting rid of things like annoying ringings or like background noise or like fans, that kind of thing. Anything that isn't in that 300 to 3000 hertz just doesn't matter. I mean, you can see if I swap between them. It does get smaller. It's because there's less audio there. We've got rid of some of it, but it's also less wibbly wobbly. There's a lot less of these kind of big changes up and down, especially like over here. You can kind of see everywhere. That's the first step. That gets it to be much more flat. It gets it to be just the stuff that we care about, just the audio, just the human speech. The next step is to run an absolute filter on it. To do that, essentially what you do is just take the absolute value of every sample. So if it's negative, it becomes positive by the same amount. And that looks like this. I think you can probably see where this is going now. This is starting to look like a graph of how loud it is at any given moment. And pretty much what we do next is do a mean. So the way that this works, I mean, this is an implementation limitation here. Like ideally, I would much rather just have a moving average, but the Web Audio API forces you to do everything in 128 sample blocks. Because I didn't really care, I just said, just average each 128 samples. We get this nice little graph that shows you how loud it is at a given time. Take that one step further and we just amplify it so that it goes between 0 and 1. Now we have what looks like a pretty good graph of how loud the audio was at any given time. So that is where Chrome thought the speech ended, that vertical bar. What I've also put in there is these two horizontal lines, the red and the green. And these were just kind of manually played around with and decided on. Essentially, I said above green is definitely speech. Below red, definitely not speech. And I put those at 3% volume and 20% volume. So that's 3% and 20% of the peak volume after we've normalized it. So it accounts for the fact that some people are quieter. What we do is we slide the speech recognition API's guess of where it ended back until we get to a sample which is definitely speech. That is our like lower bound. It's definitely still going at this point. Then what we do is we run that forwards until we've heard silence for a long enough period of time. So in this case, I think it was like half or 50 milliseconds or something. Basically, I don't want the short pauses in between like words in a sentence to trigger it to stop. So it moves forwards until it's had enough silence that it's confident that you've stopped talking. That's our upper bound. That's the absolute latest that the actual stop could be. Then what we do is we slide it backwards again until we slide it backwards again to the start of that silence. What we end up with is essentially we've said the first period of silence. So we place our actual endpoint at the start of the first period of silence after the last bit of guaranteed speech before the initial guess. Essentially, we just shift it backwards and forwards a lot until we're happy with where it is. There's not a lot of science in this. There was a lot of trial and error until I found something that worked. But if you play around with it yourself, I hope you'll agree, it does work. It's really, really pretty good. And before I added all of this, it didn't work nearly as well. It would often cut the start and end off. So yeah, in this case, there's not that much difference between our version and Google's. But there have been cases where my internet lagged for a second and the original end time was off by 5 whole seconds. And this technique avoids all of that. For the start time, we do the exact same thing, just flipped in reverse. So we move it backwards in time and then forwards in time rather than forwards and backwards. It's quite simple. So now that we've done that, we know the start time and the end time of the speech. We also know what was said. We know what was said. We know that it's recorded. We know that it's doing all of that. And that's pretty much it for that second page. I've pretty much explained everything. And to celebrate, what I'm going to do is come in with a second demo. I'm just going to do the exact same thing that I did at the start. But what I want you to do is to just watch and bear in mind all of the stuff I've just talked about. Just bear in mind how much is going on under the hood. So one of the things we talked about, that speech recognition API, the audio started, speech started events. That's what these lights are. Red light means that the speech recognition API has audio started. It's currently recording. You can see that when I stop my sentence, it goes off. That's because it's finished seeing that sentence, and then it just restarts it. You can see the green. That is saying that it's detecting speech. So not until I start talking does that actually come on. And that's kind of Google's servers and the speech recognition API saying that it's detected speech. It does get a little bit upset if you talk over the boundary when it's stopped. So I don't know if you noticed the first time, I was taking kind of a second between sentences. But as long as you do that, it does work pretty well. So I'm just going to go through this again. And yeah, as I said, it is recording this whole time. All of this is recorded, and I can show you it as well towards the end. But let's actually go through and record these lines. The script to use in my tech talk. I didn't like that. I'm going to say it again. So remember the Levenstein distance, the pronunciation? It's looking at what it hears written down here. It's comparing that to this and this based on pronunciation. In that case, neither of them were below that 0.5 or they overlapped, so it didn't pick either. The script to use in my tech talk. This is the text I'm going to read aloud during my tech talk. It's not the most interesting text. I didn't like my delivery of that one, so I'm going to say it again. It's not the most interesting text. Nevertheless, I think it should serve to prove a point. Now, hold on to your hats because we're about to see something crazy. Now hold on to your hats because we're about to see something crazy. This is a new paragraph. Wow. Oh, that was what it was. I didn't mean to do that. Wow. Truly innovative content this is. Completed. So it runs through all of those. And yeah, as promised, I said that I would show you the fact that all of that talk that I did at the start, it's all just one audio file. All of this is the talk that I was doing at the start. The only thing that's outputting is the timestamps. And it's just cutting bits of that from this. I have no idea which bit of that it was meant to be using, so I don't really care because you can't hear it. And of course, there's loads of tech that I want to talk about in here. It's using like WebGL and IndexedDB, and it's written in Svelte, and it's all reactive, and it's using the Web Audio API. But that's a talk for another day. I think the important thing is just look at this. Bear in mind what I just did. I just sat there, didn't touch the keyboard and mouse, talked to it, and then all of that I've just talked about was actually looking at when I started, when I ended, and picking out these times, and then kind of has done this. And if I click download there, well, there we go. It's an audio file. So let's, I think we're just wrapping up now, really. Yeah, conclusion. Web browsers have a load of really cool experimental APIs. Speech recognition is really cool. The WebGL is not really experimental anymore, but the one that I was using was really cool. It was rendering, that waveform there is rendered in full detail. There's no like picking out samples. When I say 44,100 samples per second, it's drawing 44,100 lines per second of footage. And it does that because it's on a graphics card. On a CPU, it's really slow. University is useful. Crazy. Yeah, there are definitely some bits which I do use, like Levenstein distance. Not to say I couldn't learn them elsewhere, but I'm glad to have to know it. And finally, if you can explain in detail how humans would solve it, how humans would detect speech, it's just loud and then it's quiet. How humans would detect when two sentences were similar, it's when they sound the least different. Just write that down step by step in JavaScript, and it'll probably work. There are often kind of, you have to backtrack, you have to change course, but you can usually get there. So thank you all very much for coming along and listening to my talk. I hope that you all enjoyed it. And I've got the mandatory page full of plugs for my things now. So yeah, I'm on GitHub. So is Narration Studio. It's MIT licensed, free and open source software. So feel free to download the code and then sell it to people. You're legally entitled, or ideally contribute with issues and PRs. I'd prefer that, but I'm not going to stop you from just selling the code. Follow me on Twitter. You can get in touch with me via email, or there's the link to my website as well. It's a mostly outdated blog, which I've always intended to fix. Go play around with Narration.studio. Maybe it'll be useful for a project that you're doing. Maybe not. Add narration to your blog posts. I enjoyed it. It was fun. People seem to like it. Go check out the Down the Ergonomic Keyboard Rabbit Hole blog post. It's really good. And most importantly, come and watch me do live programming on Twitch. Yeah. Is that? Yes. Those are up there. That's good. That's done. Does anyone have any last questions or anything else that they want to know about? Because now is your last chance, unless you email me. So ask away. And thank you very much.
How often do you stream on Twitch? Do you kind of try and keep it regular, or?
At the minute, not as much as I wanted to. For a period, it was live coding every day. And even like Narration.studio was mostly developed live on Twitch. So at the minute, it's probably once or twice a week. But you can follow me and you'll get emailed. I'm going to be honest, I mostly play RuneScape, so look forward to that. But maybe there'll be some programming.
Have you got any like projects in the pipeline for that, or anything to?
There's always bits and pieces. There's just a never-ending list of things that need doing, really. So like with streaming on Twitch, there's all of the overlays and things are done dynamically with websites and just added in as browser sources. So all of that's custom made and doing alerts and things. That's been a big kind of long-term thing. In terms of smaller projects, there was definitely something I was working on, but I've forgotten. So yeah, follow me on Twitch and maybe you'll find out.
Random question on the audio analysis stuff that you did, like the start and end detection. If I recall correctly, maybe I listened at university a little bit, you need to do a Fourier transform on that to find the frequencies. Is that, did you have any, was it fast enough in JavaScript? Because that was always the problem with digital signal processing, was being able to do that stuff fast enough to keep up in real time. That was my first question. The second one was, when you do the, when stuff gets sent to the Google speech recognition API, does it like respect the locale headers and figure out whether this is a ENGB type person speaking or an ENUS type person speaking. Fabulous talk, by the way. Really, really clever stuff.
Thank you. Yes. Okay. So first question, it does need to do fast Fourier transform. It needs to do all of that. It needs to do frequency analysis. What I'm using for all of this is something which so a previous project of mine was called Muse Tree, which was to do with like AI generated music and playing that in the browser. I used my knowledge of the web audio API that I got from there. So pretty much there's a web audio API in JavaScript in browsers, which is better supported than this, works in Firefox and everything, which is essentially designed for real-time signal processing in JavaScript. This is actually easier on it because I'm not doing it real time. I'm doing it, you know, I mean, you see after I say completed, it goes through this little process of like, you know, like saving audio, you know, processing audio, extracting timestamps or whatever, something like that. And it's at that point, like it's doing it just synchronously, not in real time. So I wasn't too concerned about it. I'm pretty sure that under the hood, the web audio API is using like native implementations of all of that. But even if it wasn't, I think JavaScript is impressively fast now, especially in kind of Chrome, which is the only thing that you can use Narration.Studio in. So I never had any issues with it. The only times I did have issues with performance in the web audio API was working on Muse Tree when I had things like, so I made a piano implementation entirely out of like oscillators, filter banks, reverb, that kind of thing. And that was using like 20 or 30 filters, like bandpass filters, filter banks, that kind of thing, per note of piano, when it was playing like 15 or 20 notes per second. Then it got quite slow, but this is going nowhere near that.
That's why 1980s keyboards like only let you press 4 keys at once, right?
Yeah, exactly. It's constantly amazing, just like how powerful computers are now. The fact that it can do stuff like that. The fact that I actually went through this, I mean, this is kind of the third screen. I wasn't really going to talk about it, but I went through a whole process of trying to get that, trying to get this whole like, you know, timeline waveform to run fast enough to get it to work. I was using, like, I started off using just divs and like SVGs with lines. I was doing all kind of destructuring the data, taking out every, you know, only keeping every 1,000th sample. And then I gave up on that, used Canvas. And then I gave up on that and I used WebGL, and I was still using all of the kind of time-saving hacks that I'd done, where I was like pre-rendering them and then only re-rendering them when they needed to. And all of that was really slow and really inconvenient. And literally what it is now is that is one canvas which is being drawn by the GPU. There is no pre-processing done on the data. It just draws the entire audio file onto the screen, like the relevant bits as a waveform. So it's drawing an insane amount, and there is just like no noticeable lag. I've got a 165 hertz monitor and it just works perfectly, like at 165 hertz, which just astonishes me. But yeah, definitely a tangent there. Let's see if I can remember the second question.
The locale stuff.
The locale stuff, yes. The speech recognition API does take locale information. So it has a lang flag that you can pass in. It's part of the spec. Frankly, in this this API, I wouldn't trust the spec because nobody implements the spec. Chrome comes closest, but yeah, you can pass in just like NUS. That's not automatically taken from the system, and frankly, I don't know which one I'm using. I imagine I'm probably using NGB in Narration Studio and didn't put much more thought into that because it was kind of just a one-off project. But yeah, you can quite easily change that to whatever language you're using as long as it's supported by your browser. Obviously, it wouldn't work to put in like French because we're still using the CMU pronouncing dictionary So you'd need a separate dictionary for French and probably a different set of like phoneme mapping. But there's not a lot to change to make it work in different languages.
No, that's cool. I was thinking more about the locale rather than the language, because I've messed about with this for some. My other half's a journalist, and I tried to do something to avoid having to transcribe interviews. But
my wife's currently doing a PhD, going through the same thing.
Yeah, it's quite hard.
Yeah.
But changing the locale flag, at least from US English to British English, if you've got a British subject, makes it a little bit easier.
Yeah. Completely off topic, but what I did for that with actual transcription, because transcription is kind of going the other direction. On this, it doesn't matter if we're not very good, because we know we're only looking for one of two things. And if it's not there, if it doesn't pick up that you've tried to say one, you'll just say it again. Whereas if you want to go from just text to transcription, on Google Cloud Platform, they have access to their speech recognition API. It's significantly better than this, and it's got custom models for things like phone calls, videos, multiple speakers. So I built just like a little framework around that for my wife, which worked a bit better. That's a thing that I worked on another side project, was kind of a reverse of Narration Studio, where it looked at the examples and kind of let you edit the transcriptions together. Very off topic. But yeah, basically, have a look at the Google Cloud Platform, was it like GCP speech to text?
Yeah, that's what I was using. It was good, but the thing is that the difference for somebody who wants to use it for an interview transcription between 80% right and like 99% right is quite a lot. So
yeah,
that was where I got stuck.
It's definitely kind of had to build that tooling around the fact that it wasn't going to be perfect. So kind of the way that I handled that was looking at getting multiple, and so I'd ask it for the multiple options of what could be said, and then do like string similarity again, so that it would kind of give you the options to choose from. But it's not quite there.
Thank you, though. That was great, and some great ideas on that from, like you say, the looking at Levenstein distance and then using phonemes on that. That's really clever.
I think that was definitely the core nugget there. I think that took it from barely working to being impressively good. Is there anyone else? Any other questions? I'm happy to talk. I don't know if I've made that abundantly clear yet.
Cool. Okay then. If there's no questions then. Brilliant. No, yeah, awesome talk. Really enjoyed that. I'll take the screen off you just for a second.
Yeah. Thank you very much. I had fun. I'm glad that I had a drink, I'm going to be honest, because I can feel my voice going already.
For a second, I thought it was Red Bull, actually, when you were sipping out of a can.
No, it's dilutable Vimto. Drink of kings.
Right, if I can find my screen. There we go. Cool. So, yeah, like once again, yeah, just a big thanks, Steven. Awesome talk. If anybody wants to get in touch with them, I know you had a screen with 1,000,001 different social media plugs, but yeah, I guess there's a couple of them there. If you can't remember any of them, then you can get in touch with any of us at Any Tech, and yeah, we can certainly forward your questions on, or if you have any questions around Any Tech, do get in touch. Easiest way, like I said, just go to any.technology, and all the social media stuff is there. Next month, we kind of I guess we're keeping on the topic of sort of speech recognition. We've got Cameron Trotter, who is studying a PhD at the moment in basically conversation in marine animals. So he's using machine learning to kind of understand how dolphins speak to one another. So yeah, definitely get yourself signed up to that next month.
That sounds awesome. I'm glad that I wasn't having to try and follow that up.
Not only that comes perfectly in tandem, to be honest. Yeah, so I guess all that's left to say is just a big thanks to everybody. Big thanks to yourself, Stephen. Yeah, awesome talk. And yeah, we'll hopefully see everybody next month. Thank you all.
Thank you very much.
Cheers.